Greetings and welcome to the introduction to astronomy. In this lecture video, we will talk a little bit about astronomy and science. So some of the things that we look at in an astronomy course, some of the different objects that astronomers study, and then why do we want to study astronomy at all? And what do astronomers use the scientific method? We want to discuss how that works in astronomy and in general. So those are a few of the things that we're going to go over in this lecture. So let's start off with, first of all, what is astronomy? Well, most simply put, astronomy is the study of the universe and everything in it. So anything that we see in the universe is part of the study of astronomy. I've given a number of things here that are included, but anything within the universe, it's not a comprehensive list. There's a lot more that could be studied. So let's start off looking at one example, and that is an example of a planet. Within our solar system, we have planets and moons that we study in astronomy. And here we have an example, and this is the planet Mars. Mars has some interesting features. We see some great volcanoes over here on the side that are present, not currently active, but that have been active in the past. We see a great rift valley here that we call Valles Marineris. So a great rift in the crust of Mars that would stretch across our entire country and across the entire United States if it were here on the Earth. So an incredibly large valley there. Mars also will have polar caps and does have a thin atmosphere as well. There are, of course, lots of other planets and moons that would be studied as well. But here is Mars as one example of objects that are studied by astronomers. Now also we study not only within our solar system do we have planets and moons, but we also have comets and asteroids. So here's an example of a comet, and we see on the comet a number of different features. We see the head or coma of a comet, and that's here at the front, which is this outer layer, outer region here. That is the head of the comet. And then we see the tail or tails. In most cases, a comet will have two tails stretching back away from the sun. Comets are essentially an ice ball that maybe is the size of a city, a few miles across. And when they get close to the sun, the material gets vaporized and forms the head and the tail. Comets, like planets, are one of those objects that have been known to people since ancient times. But of course, with modern technology and being able to actually go visit these objects, we have a much better understanding of them today than we did hundreds of years ago. Now, not everything we study in astronomy is within our own solar system. We also look at other objects, and that would include things like stars. Stars, a picture of an individual star doesn't look like much because stars are so far away that even to the largest telescopes, they just look like points of light. So this is an example of a star cluster that we see. So a cluster of stars, or a grouping of stars, here taken by the Hubble Space Telescope. Stars can be grouped together in clusters. They can be alone by themselves, pretty much like our own sun. And they can be grouped together in larger groupings. But star clusters would be a part of an example of what we'd see within a galaxy. So that leads us to our next slide that shows us a galaxy here, and this is an example of a spiral galaxy. So galaxies come in different types, and spirals are one example. Our own galaxy is a spiral galaxy, and you can see coming from the central portion here that there are spiral arms that stretch out and around the galaxy as it sits here. So we see those spiral arms. That's where a lot of the stars are forming within the galaxies. We would also see star clusters forming within the galaxy, as well as other objects that we would look at. There are also different types of galaxies. A spiral is one type of galaxy, but there are also other types of galaxies that we see, including things like ellipticals and irregular galaxies that astronomers would also study. As we look at others, one of the other things that we can see is nebulae. So within the galaxy, there are also nebulae. Nebulae come in different types. This is one example, and this is an example of a supernova remnant. So what we have here is the remnant of a supernova that occurred a long time ago. And this is the remnant of it, not seeing the supernova of itself, but we are seeing the remnant, what the material left behind. And what happened visible here on Earth in 1054 was a really bright star, what we called a supernova. Nova is a new star, and a supernova was an extremely bright new star and became one of the brightest objects in the sky. And a supernova can actually be visible during the daytime. And in the nearly 1,000 years since this supernova was seen to occur, the material has been expanding outward, and you see the filaments and structures within that nebula as it expands outward, as it has been doing so for nearly 1,000 years now. Now at the center of this nebula in this case would be a neutron star, the collapsed core of the star left behind, the mass of the sun, or even a little bit larger, and the size would be the size of a city, maybe about 6 or so miles across. So compacted down to extremely dense levels, not quite a black hole, which is our next topic, but very, very close to it, and something that we call a neutron star. Now, as I said, black holes were the next thing to look at. So let's look at the black hole here. How do we get an image of a black hole? Well, we don't. This is actually an artist's conception or drawing of what we believe a black hole would look like. So the black hole itself is invisible because it is matter that has condensed down so much that even light cannot escape from it. So nothing escapes from a black hole because nothing can travel faster than light. However, outside what we call the event horizon of a black hole, which is the point from which light can no longer escape, again, we call that the event horizon. Then when we're further out than that, then material can escape. And here we're seeing, as the artist conceives, and some black holes seem to be doing, that material is being pulled from a companion star and then spirals in and around in towards the black hole. That gives the black hole a source of energy, and then allows us to see the material around the black hole as it is heated up to incredibly high temperatures. So as this material spirals in, it's heated up to very, very high temperatures, and that allows it to give off radiation that can then be detected. Once it crosses this event horizon, we can no longer get any more information about that black hole. And these are just some of the objects that astronomers study, and not a complete list by any sense. There are a lot more objects that we will study and that one would study if taking a class in astronomy. So why? The next question would be, why do we want to study astronomy? Other than learning about all of these interesting objects that we've looked at, why would we want to study this? And studying astronomy or any other science really teaches a way of thinking. And that's an important thing, is that it's a different way of thinking and a way to critically analyze information and then even apply that to everyday situations. So what we'll look at coming up here in the scientific method is a way of thinking about things and how things work, not only in the universe, but even in everyday life. It also gives us a broader understanding of the universe. So even though I know that most students who take my astronomy classes are not going to become professional astronomers, however, it hopefully teaches them a way of thinking and gives them an understanding of appreciation of the universe. So let's look a little bit at the scientific method here and what we mean by scientific thinking. And scientific thinking uses a couple of definitions here, just a couple of things we want to look at first. And that would include some of the terminology, like the idea of what we mean by a theory. Sometimes you think of a theory as, oh, it's just a guess, but it really isn't. Theories are based on observations and studies. So things that have been have survived many tests. So an example of a theory or a hypothesis that would be a a good one would be something that is testable. That is the most important thing in a theory, is that it has to be some way to test it. If we come up with a theory that Einstein was the greatest scientist in the history of mankind, then that would not be something that we have any way to test. It's not something that is testable. Or the Mona Lisa is the greatest painting ever done. That is not something we can test. It is a matter of opinion. An example of something that we could test as a scientific hypothesis would be that the moon is made of green cheese. We may know that as a ridiculous statement now, but it makes perfect sense in terms of being testable. We could take a trip to the moon, send a robotic probe to the moon, get a sample of the material there and find out what it's made of. Now, of course, we've already done that, so it's less of a scientific theory now than it was, for example, in the past. But it is an example of something that could be tested. We also use models in astronomy. Models are ways of simplifying how things work. So for example, we looked at a galaxy. In order to understand a galaxy and its motions, we have to understand how the matter is distributed in it. We cannot possibly model exactly how the matter is distributed. So we have to make assumptions and approximations as to how things work. We use this in a number of cases, ways of simplifying how things are, to be able to make us better able to model them, simply because it is not possible to model to calculate the exact position of every atom within a galaxy to be able to figure out how it's going to work. We have to make specific assumptions, and that's what we mean by a model. And we have to take that into account when we think of how things are determined from models, that we did make a number of simplifications going into them, and that may have an impact on our final results coming out of the model. Now, coming back to hypothesis, we've kind of looked at that when we talked about theory. The difference between a theory and a hypothesis is that a hypothesis is more the moon is made of green cheese up here, that we've just given some general idea as to, maybe this is what the moon is made up of. Whereas a theory is something that has been tested over and over, something like the theory of relativity, something that has been significantly tested and tried over a good period of time. But a hypothesis, again, is a proposal that we'll give to explain some observation that we see. So an example here is we see the observation, something that we don't debate, is that the sun rises in the east every day. What is open to interpretation is why that occurs. So this is the observation that we see, and this is the possible explanation. Why does it occur? And the sun orbiting the earth, or we may want to say that the earth spins. A completely another example of how we can explain that the sun rises in the east and sets in the west every day could be that the earth is spinning. And each of these would make other predictions, and you would then use that to test your hypothesis and find out which one best supports it. And this all leads us to this idea of the scientific method. So we'll look at the scientific method here. And it is, again, a way of thinking. So it has a starting point. It starts with some observation that is made, but it has no ending. So you can start it, you observe something happens, but in key, it never ends. We are always continually modifying our theories, modifying our hypotheses to have them better fit the observations, to get better models that better explain what is going on in the universe. So you start with that observation, you come up with a hypothesis that explains that observation. And as I mentioned before, the key is that it must make some kind of testable prediction, something that you can test. Once you do that, you test your predictions and make more observations. And then one of two things could happen. One is that your predictions could be found to be correct. Great. That is that's good, but you're not done. So you're not done even if this is the case. You don't stop once my predictions are correct. My predictions are correct. My model was correct. It's now perfect. And that is exactly how things work. You continue on, you make more predictions, you refine your model, try to find out where it works and possibly where it does not work. Or you may find out that your predictions were incorrect. Oops, I made a prediction that this was going to happen and something completely different happened. That leaves you with a couple of options. You can either modify the hypothesis and make adjustments to it to have it fit your observations, or you may, if things are bad enough, you might have to reject your hypothesis altogether and go back and start up over here. Let's come up with a new hypothesis that then explains not only what our original observation, but our new observations as well. So let's look at this in a little bit more of a picture form. Here's a diagram that kind of shows the scientific method and the process that is used. And it starts off with exactly what I've shown you on the previous slide. You start off up here with making observations. You formulate your hypotheses. What kind of hypothesis will explain the observations that you saw? Then, as I said, the key is to develop testable predictions and then make more observations to test those predictions. Then here's where things go over and over again. You may have to make refinements and alter your predictions. You might have to reject your hypothesis altogether, in which case you actually come back here and come up with a new hypothesis. And then you develop new testable predictions. So this cycle right here is continually ongoing. Once this has gone for a while and you've got very good thoughts and very good ideas, then you may end up with a general theory that explains a lot of the things that you were looking at. Although even at that point, again, it's still an ongoing process and you continue to test what is happening here. And that you make further observations and you may find more hypotheses. Maybe you will confirm your theory. Maybe you'll find some regions where your theory does not work and you need to modify your theory and or modify your hypotheses to come up with a new, better theory and a better model. So let's finish up here with a little bit of a summary. And what we have is just a little bit about what we've looked at in this lecture. We've looked at astronomy. What is astronomy? Well, it's the study of everything. It is the study of the universe and everything in it. So everything from the Earth out to the edges of the universe is a part of studying astronomy. Why do we study astronomy, other than maybe to get our science credit that we need to get, is to learn a scientific way of thinking that can be applied in everyday situations. And then finally, we looked at the scientific method, which kind of is that way of thinking that we want to emphasize. And it is a never-ending process. So it never ends. You start with some observation, but you continually make more and more observations to allow scientists and us to continually modify and improve the theories and the models that we have made, so we can better improve those to be able to make better predictions and help us to better understand the universe. So that concludes this lecture on astronomy and science. And I hope you've been able to get some good information out of it and get a little bit of a beginning understanding of astronomy. So until next time, have a great day, everyone, and I will see you in class.